There is something strange about the largest river on Earth. Humans have built bridges across enormous bays. We have connected islands to continents. We have built bridges over deep ocean channels, earthquake zones, frozen seas, and valleys so wide that the opposite side disappears into the horizon. But there is one place where the map suddenly seems to return to another century: the Amazon River. For thousands of kilometers, this enormous river crosses South America. Ships travel along it. Cities stand on its banks. Millions of people live throughout its basin. And yet, across the main channel of the Amazon River, there is not a single bridge, not one. If you want to reach the other side, you use a boat. That sounds almost impossible. We live in an age where engineers can drill tunnels beneath the sea and build structures hundreds of meters above the ground. So why has nobody simply built a bridge across the Amazon? At first, the answer seems obvious. The river must simply be too wide. But that explanation is wrong. Humanity has crossed wider stretches of water. Then perhaps the current is too powerful. That is part of the problem, but it still does not explain everything. Maybe the rainforest is too remote, closer. But even that misses the strangest part of the story. Because the real reason there are no bridges across the Amazon has less to do with the river itself than with what exists on both sides of it. And by the end of this journey, you will see why building the bridge might actually be easier than building everything a bridge would need around it. To understand the problem, we first need to forget the Amazon we normally see in photographs. Most images show a clearly defined river, brown water in the middle, green forest on both sides, two banks, one channel. It looks like any other large river, just bigger. But from above, the real Amazon is much more difficult to define. The river is not simply a line of water crossing a forest. It is an enormous, moving system made of channels, islands, lakes, flooded forests, sandbars, and wetlands. During part of the year, areas that look like land become water. Channels grow wider. Lakes expand. Forests flood. Islands can appear to shrink as the water rises around them. In some parts of the basin, the difference between the dry season and the wet season changes the landscape so dramatically that it can look like two different places. This creates the first problem for anyone trying to build a bridge. Where exactly does the river end? Imagine an engineer arriving during the dry season. The main channel might seem manageable. You identify one bank, you identify the other, you calculate the distance, you design the bridge. Then the rains arrive. Water rises. The surrounding lowlands begin to flood. The river spills into side channels and lakes. Forests become part of the river. The narrow crossing you designed in the dry season is suddenly sitting in the middle of a much larger aquatic landscape. In some regions, the floodplain surrounding the Amazon stretches more than 30 kilometers across. That means the challenge is not always building a structure over one channel. The challenge may be crossing an entire floodplain. And a floodplain creates a completely different engineering problem. A conventional bridge normally begins on solid ground. It supports transfer enormous loads downward. The road approaches the structure from stable land. But in the Amazon, some of that land spends part of the year underwater. So even after the main bridge ends, the road may still need to continue across wetlands, secondary channels, and seasonally flooded terrain. You might need elevated sections, long embankments, drainage structures, additional bridges, and kilometers of reinforced road just to reach the bridge itself. Suddenly, a project that looked like one bridge becomes an entire transportation corridor. But water is only the beginning. The Amazon is also carrying something with it: sediment. The river receives enormous quantities of eroded material from far away, including sediment carried eastward from the Andes. That mud, sand, and fine material does not simply disappear into the water. It is constantly being moved downstream. Some of it settles, Some of it is picked up again. Sandbars form, channels shift, banks erode. The river is constantly reshaping the landscape through which it flows. This is normal behavior for a great river. But for engineers, movement is expensive. A bridge wants predictability. You want to know where the deepest channel will be. You want to know where the strongest current will pass. You want stable ground for foundations. You want the riverbank to remain approximately where you found it. The Amazon does not always cooperate. A bridge pier that seems safely positioned today must survive decades of changing flow conditions. Water may scour sediment from around its foundation. Channels can change the way current attacks a structure. Floating debris can strike supports. And every element must continue functioning through repeated cycles of flood and lower water. None of these problems is impossible. Engineers solve similar problems around the world. But each solution adds complexity, stronger foundations, deeper piles, larger spans, more protection against erosion, more monitoring, more maintenance. And the structure has not even reached the most difficult question yet. How high should it be? The Amazon is not just a river used by small boats. It is a transportation system. Large vessels travel enormous distances through the basin. Ocean-going ships can move thousands of kilometers inland. That changes bridge design completely. If a bridge is too low, it blocks navigation. If the central span is too narrow, it creates risk for shipping. So a major crossing would need enough clearance for vessels beneath it while also stretching across a huge and seasonally changing river system. To gain that clearance, the roadway has to climb. And when a road climbs, its approaches become longer. Now imagine trying to build those approaches across flooded forest. The bridge becomes longer. The road becomes longer. The foundations become more expensive. And the project begins expanding far beyond the original river crossing. This is why simply measuring the width of the Amazon gives the wrong impression. The visible water is not the entire project. The real bridge begins kilometers before the river and may continue kilometers after it. But if all of these problems are engineering problems, then there is an obvious question. Surely a wealthy modern country could still build one if it really wanted to. The answer is yes, and we already have proof. Near Manaus, one of the largest cities in the Amazon region, there is a huge bridge crossing the Rio Negro. The Rio Negro is one of the Amazon's great tributaries. The bridge connects Manaus with communities on the opposite side and demonstrates something important. It is possible to build a major bridge in the Amazon basin. The technology exists. The materials exist. Engineers know how to work in this environment. But the Rio Negro Bridge also reveals the real reason the main Amazon remains bridge-free. A bridge only makes sense when there is something important for it to connect. This sounds obvious, but it changes everything. Think about bridges in Europe, North America, or Eastern Asia. A major river may have highways on both sides. Cities exist across from one another. Factories need trucks. Commuters travel every morning. Railways move freight. Road networks already exist. The bridge is the missing link between two transportation systems that are already there. Remove the bridge and traffic has a problem. Build the bridge and the network becomes complete. Now look at huge sections of the Amazon. The situation is almost reversed. In many places, there is no dense road network waiting on the opposite bank. There may be forest, small communities, protected lands, wetlands, rivers, and enormous distances before the next major road or city. So imagine spending billions of dollars to cross the river. The bridge reaches the opposite bank. And then what? You still need a road, not just a few kilometers. Potentially, a completely new transportation corridor through the rainforest. That road needs drainage, maintenance, bridges across smaller rivers, fuel stations, connections to towns, emergency services, and enough traffic to justify everything that was built. This is where the strange logic of the Amazon becomes clear. In most places, rivers interrupt transportation. In the Amazon, the river is transportation. For centuries, people in the region have used waterways the way other parts of the world use highways. Boats carry people. Boats carry food. Boats carry fuel. Cargo moves from settlement to settlement along the water. Large cities developed around access to rivers because the river itself provides the route. From the perspective of someone looking at a roadmap, the Amazon appears to be an enormous obstacle. From the perspective of someone traveling through the basin by boat, it is the opposite. It is the road. And this explains why the Amazon can support major cities despite having relatively few bridges. Manaus is one of the clearest examples. It is a huge city located deep inside the continent. Yet the river allows large cargo vessels to reach it from the Atlantic. The same water that seems to isolate the city on a road map connects it to the outside world. That is difficult to understand if you come from a place where transportation developed around roads. We instinctively look at a river and ask how to cross it. But the Amazon developed around a different question. How do we travel along it? And that changes the economics of a bridge. A bridge is not built because engineers can build it. A bridge is built because enough people and goods need to cross at a specific place to justify the cost. There are parts of the Amazon where ferries are simply more practical. A ferry adjusts to changing water levels. It does not require a continuous structure across the entire floodplain. If traffic demand changes, boats can change routes. If a settlement grows, more vessels can be added. The system is flexible. A giant bridge is the opposite. It is fixed. Once billions are committed to one crossing, the road network must justify that exact location for decades. And this brings us to another obstacle that does not appear in engineering drawings: the forest itself. Building a major bridge would rarely mean building only a bridge. The project would likely require access roads and improved highways leading toward it. And roads have consequences in the Amazon that go far beyond transportation. A road opens previously difficult to reach land. Once access becomes easier, other activities can follow: new settlements, logging, agriculture, land clearing, mining, secondary roads. Development spreads outward from transportation corridors. This is one reason major road projects through the Amazon attract intense debate. The environmental cost may extend far beyond the strip of asphalt itself. A bridge across the main Amazon could therefore create an unusual paradox. Its largest impact might not occur over the water. It could occur deep inside the forest on both sides. This means governments considering such infrastructure have to calculate more than concrete, steel, and traffic. They have to think about ecosystems, protected areas, indigenous territories, deforestation, long-term development patterns, and whether the economic benefits of a new road corridor justify those risks. Now we can see why saying the Amazon is simply too wide for a bridge is misleading. Width is dramatic. But width can be solved. Long-span bridges exist. Deep foundations exist. Cable-stayed structures exist. Construction barges exist. Modern engineering could design a crossing. The real difficulty is that every engineering solution makes the economic question harder. A wider floodplain means more construction. More construction means greater cost. Greater cost requires more traffic to justify the investment. But many remote regions do not generate enough road traffic. Creating more traffic requires building more roads. More roads increase environmental impacts and maintenance costs. And suddenly, the project enters a loop. The bridge needs roads to make sense. The roads need development to make sense. But that development may create exactly the environmental damage society is trying to avoid. This is why the absence of bridges is not a sign that the Amazon defeated modern engineering. It is the result of geography, economics and transportation evolving together. And there is another clue hidden in the way cities are positioned along the river. If you examine other great rivers, major cities often grow on both banks. London occupies both sides of the Thames. Paris spreads across the Seine. Cairo occupies both sides of the Nile. Bridges become essential because everyday life occurs on both sides. Workers live on one side and work on the other. Roads intersect the river. Urban expansion demands constant crossings. In much of the Amazon, cities historically grew with the river rather than across it. Waterfronts became ports. Settlements faced the river. Commerce moved along the river. The transportation geometry is different. Instead of a road meeting the river at 90 degrees, the main transportation route may run parallel to the water for hundreds or thousands of kilometers. There is less reason to cross simply for the sake of crossing. But what would happen if someone decided to build the first bridge across the main Amazon tomorrow? First, engineers would need to choose the location very carefully. They would search for relatively stable banks. They would study the riverbed. They would map seasonal flooding. They would model currents. They would calculate navigation clearances. They would investigate the geology beneath layers of sediment. Then they would have to design foundations capable of surviving enormous hydraulic forces. The structure would need to withstand years of floods, debris impacts, corrosion, and changing river conditions. Construction materials would have to be transported to a region where logistics are already difficult. Workers would need access. Equipment would need staging areas. Temporary docks might be required. And all of that would happen before the surrounding road system was fully completed. Then come the approaches. A bridge cannot simply drop vehicles into the rainforest. Roads would need to connect the crossing to existing population and economic centers. Those roads might cross dozens of smaller waterways. Each one creates another engineering project. Drainage is critical in a landscape receiving enormous rainfall. Maintenance would never stop. Vegetation grows quickly. Floods damage surfaces. Remote sections are expensive to repair. What looked like one bridge on a map has now become hundreds of kilometers of infrastructure. And this leads to a surprising conclusion. The hardest part of building a bridge across the Amazon may not actually be crossing the Amazon. It may be reaching the bridge. This is why looking at satellite images can be misleading. You see one blue line, you imagine connecting 2 points. But the Amazon is not one blue line. It is an entire landscape organized around water. The river, tributaries, floodplains and forests function together. Trying to force a road network across that system is much more complicated than simply placing steel above a channel. And yet the story may not remain this way forever. The Amazon basin is changing. Cities grow. Transport demands change. Road projects continue to be debated and constructed. Extreme droughts can temporarily make river navigation more difficult in some areas. Economic pressure for more reliable land transportation may increase. And at some point, a location could emerge where the benefits of a bridge outweigh its enormous cost. If that happens, humanity could build one. The absence of bridges is not a permanent law of physics. It is a choice created by current geography, economics, and infrastructure. But if the first main channel bridge is ever constructed, it will represent something much larger than a piece of engineering. It would mark a fundamental change in how humans move through the Amazon. For thousands of years, the rivers have determined the routes. Settlements followed the water. Trade followed the water. Exploration followed the water. Even modern cities depend on the water. A bridge would do something different. It would tell the landscape that, at one specific point, the road no longer intends to follow the river. It intends to cross it. And perhaps that is the real reason the Amazon has remained without a bridge for so long. We normally think of a bridge as a symbol of connection. But in the Amazon, the river already provides the connection. The water is not simply an obstacle dividing two sides. It is the highway joining thousands of communities across one of the largest river systems on Earth. That is why the map looks so strange. It is not a place where humans forgot to build bridges. It is a place where transportation evolved around something completely different. Elsewhere in the world, we build bridges because rivers stood in the way of our roads. In the Amazon, the river came first, and for much of the region, it is still the road. If you enjoy discovering why familiar parts of our world work completely differently from what they seem, subscribe to the channel. Because sometimes the strangest engineering mystery is not why something was built. It is why nobody needed to build it at all.